Hi, I'm Jen and I am a PhD student over at ICRA UWA. I'm in my last year now, where I've been supervised by Luca Cortez and Danae Labreshkov, studying the connection between angular momentum and gas fraction in both observations and in simulations. So first of all, arguably some of the most fundamental properties of galaxies are their mass and their gas content or their fuel for star formation. And I think as well, angular momentum is also a very fundamental property, and this is because it's linked to a galaxy's formation, evolution, and its morphology. So one way that we can study angular momentum is through scaling relations, and in particular the Four relation, which is the relationship between a galaxy's stellar mass and its stellar-specific angular momentum. So here I'm showing a sample of galaxies from the X-gas survey, which is a really deep H1 survey, and we're showing the relationship between these two properties. And we can see that there's a nice tight correlation by the best fit line, which is the thin black line, and also the median, which is shown by the thicker black line. So we see that there's this nice strong correlation between the two, and previous works have often looked at this relation and looked at the scatter of this relation and found that it's related to things like morphology, Boltzmann total ratio, stochastic index. In my work, I went and looked at how this related to gas fraction, which you can see as the color coding here, and we see that there's a nice strong correlation between where galaxies lie and the color coding here. To quantify this more, we can also look at the vertical offset of galaxies from this relation on the y-axis against their H1 gas fraction, and again we see this nice strong correlation between the offsets of galaxies and this H1 gas fraction. So this isn't exactly a surprising result, as works such as galaxy stability models, like the Abreshkov 2016 model, predict a relationship between gas fraction and angular momentum. In particular, the result of this stability model is that galaxy's atomic gas fraction is actually set by the stability of the galaxy, or in this situation, quantified by the angular momentum. So we decided to compare our works to this as well. So here again, I'm showing mass, but now it's baryonic mass against baryonic specific angular momentum. And now I'm actually separating into 4 even bins of gas fraction. And we can see here that the predictions from the 016 model, which is in the colored regions, I should say that the color coding is gas fraction again, we see that the model deviates from our galaxies, which are the points, particularly for low gas fractions. So we decided to fit our own planar relationship to this, and we find that in the bottom row there, that our planar fit, by construction obviously, fits a lot better with the data, but in particular it's a plane that has a shallower slope and a weaker dependence on atomic gas fraction, which is able to agree better with our data. Now this begs the question, why does our data disagree with this model when plenty of previous works have found that agreement with the 016 model? So one way we wanted to go and tackle this and find out whether our sample was weird or not was to go and look at simulations and see what they say with regards to this plane. So in particular, I went and compared to the Eagle simulations and illustrious TNG. And what we did was we extracted galaxies from these samples which were going to be comparable to our X-gas results. So we only looked at galaxies which would be H1 detected in a survey like X-gas. And we plotted them again on this same plot with baryonic mass against baryonic specific angular momentum. And we see that Eagle in blue and TNG in magenta both agree very well between these black lines, which are what you'd expect for the X-gas plane for fixed gas fractions on the edges of these panels. So we see not only that the medians of these are in excellent agreement with the plane, but also that the scatter around this plane is very similar to what we found for X-gas. So here, now I'm showing the vertical offset of galaxies from this plane as a histogram, and we see X-gas, which is the black, is very similar in distribution to TNG in particular, and somewhat similar to Eagle as well, although that is got slightly larger scatter. So this leads to 2 very interesting results, I think. The first of these being that I don't think our X-gas data was an anomaly now. I think we've seen agreement now with both Eagle and TNG as well. And also that means we're seeing a disagreement with this 016 model. The second really interesting result, which Kate gave a nice intro to, is the fact that both Eagle and TNG are actually quite different simulations. They both include models for stellar feedback and AGN feedback, all those sorts of things, but the way these are implemented are very different. So the fact of all these things hints at the fact that maybe this plane is something that's irrespective of your star formation processes. So the other advantage that simulations give us is being able to probe down into regions that we can't do with observations. So in addition to just looking at a sample that's comparable to our X-gas work, we also went and looked at all the galaxies in these simulations. And what we do when we do this, and we again looking at offsets from galaxies from the best fitting plane, we start to get this long tail emerging, which is now a population of galaxies that have very, very low gas fractions, lower than what you'd be able to detect with a survey, which is starting to deviate. So when there's a population that exists that becomes inconsistent. So I can give you an example of why this is. So again, showing my favorite parameter space, we've got baryonic mass against baryonic specific angular momentum. And this is an example of a low gas fraction bin. We start to see that galaxies start to deviate from what is predicted in the black for the X-gas plane. And I can show you a couple of other examples as well of different other gas fraction bins, even down to galaxies that have no atomic gas fraction. And we see they start to deviate quite considerably from what you'd expect from just extrapolating this observed relation down to low gas fractions. And why I think this is interesting is because it's showing us, first of all, that the distribution of galaxies in this parameter space don't seem to be changing once you get below a gas fraction of 0.01. And second of all, what it's really interesting is the fact that we're showing that the connection between a galaxy's gas content and its angular momentum is being broken in this gas poor regime. All right, so to summarize, there is a tight connection between angular momentum, mass, and atomic gas fraction, and we see this in both observations and in simulations. This connection is somewhat fundamental, as we're able to see it in both Eagle and TNG, despite their differences. And we do see that there is a difference once we enter the gas poor regime, where we're starting to see a disconnect between angular momentum and atomic gas fraction. Thank you.